Lesson: Neural Network Fundamentals, from Perceptrons to Deep Learning. Neural networks, a cornerstone of artificial intelligence, have evolved significantly from their inception as simple perceptrons to the sophisticated architectures driving today's deep learning models. This evolution is not merely theoretical, it has practical implications for professionals seeking to leverage AI technologies in various domains. Understanding the fundamentals of neural networks, including perceptrons and deep learning, is crucial for developing effective AI solutions and workflows. The journey of neural networks begins with the perceptron, a simple model introduced by Frank Rosenblatt in 1958. The perceptron is a binary classifier that maps input features to a single output using a linear function. It is the simplest form of a neural network, consisting of an input layer and an output node with an associated weight and bias. The perceptron's learning process involves adjusting its weights based on the error of its predictions, a concept known as supervised learning. While the perceptron laid the groundwork, its limitations, particularly its inability to solve nonlinearly separable problems, such as the XOR problem, prompted further research and development. This limitation was addressed by the introduction of multi-layer perceptrons, which form the basis of modern neural networks. MLPs consist of multiple layers of neurons, including hidden layers that enable the network to learn complex patterns by combining linear and nonlinear transformations. The backpropagation algorithm, a key innovation in MLPs, allows for efficient training by propagating the error from the output layer back through the network and adjusting the weights accordingly. This process is computationally intensive, but advancements in hardware, such as graphics processing units, have significantly accelerated training times. As neural networks grew deeper, the term deep learning emerged to describe architectures with many hidden layers. Deep learning has revolutionized fields such as computer vision, natural language processing, and speech recognition by enabling the extraction of hierarchical features from raw data. Convolutional neural networks, a type of deep learning model, have been particularly successful in image-related tasks. They leverage spatial hierarchies in data through convolutional and pooling layers, allowing the model to learn spatial hierarchies by convolving the input data with a set of learnable filters. The practical application of CNNs can be seen in facial recognition systems, which utilize large labeled datasets to achieve accuracy rates exceeding 95% in identifying individuals under variable conditions. To implement neural network models effectively, professionals must be familiar with practical tools and frameworks that streamline the development process. TensorFlow and PyTorch are two of the most widely used deep learning frameworks today. TensorFlow, developed by Google Brain, offers a comprehensive ecosystem for building and deploying machine learning models. Its high-level API, Keras, simplifies the design of neural networks, making it accessible for both beginners and experts. PyTorch, developed by Facebook's AI Research Lab, is known for its dynamic computation graph, which provides flexibility and ease of debugging, making it a favorite among researchers and industry practitioners alike. Both frameworks support GPU acceleration, which is crucial for training large-scale models efficiently. Real-world challenges often involve data that is complex and high-dimensional, requiring neural networks to generalize well to unseen data. Overfitting, where a model learns the noise in the training data rather than the underlying pattern, is a common issue in deep learning. Techniques such as dropout, which randomly sets a fraction of the neurons to 0 during training, can mitigate overfitting by preventing the model from relying too heavily on any one neuron. Additionally, regularization methods, such as L1 and L2 regularization, add a penalty to the loss function to discourage overly complex models. These techniques are crucial for developing robust models that perform well on real-world data. Another critical aspect of neural network design is the choice of activation functions, which introduce nonlinearity into the model, enabling it to learn complex patterns. The rectified linear unit is a popular activation function due to its simplicity and effectiveness. ReLU activation mitigates the vanishing gradient problem, a common issue with sigmoid and tanh activations in deep networks, by allowing gradients to flow more effectively during backpropagation. Variants of Ryu, such as leak U and parametric Ryu, address its limitations, such as dying neurons, and are commonly used in practice. The success of neural networks in various applications has been demonstrated through numerous case studies. For example, Google's AlphaGo, a reinforcement learning model that combines deep neural networks with Monte Carlo tree search, defeated a world champion Go player in 2016, showcasing the potential of deep learning in strategic decision-making tasks. In healthcare, deep learning models have been used to analyze medical images, achieving performance comparable to radiologists in detecting certain conditions, such as diabetic retinopathy. Despite these successes, deploying neural networks in production environments presents unique challenges. Model interpretability, scalability, and ethical considerations are critical factors that must be addressed. Interpretable models are essential in domains where decision-making transparency is required, such as finance and healthcare. Techniques like SHAP and LIME provide insights into model predictions, helping stakeholders understand and trust AI decisions. Scalability is another consideration, as models must handle large volumes of data and serve predictions in real time. Cloud-based solutions such as Amazon Web Services, Google Cloud Platform, and Microsoft Azure offer scalable infrastructure and services for deploying machine learning models. These platforms provide tools for automating workflows, monitoring performance, and managing resources, enabling seamless integration of AI into business processes. Ethical considerations, including bias and fairness, are paramount in AI development. Biased data can lead to discriminatory models, reinforcing societal inequalities. Techniques such as data augmentation, bias detection tools, and fairness constraints are essential for developing fair and equitable AI systems. Moreover, ongoing research and collaboration between AI practitioners, ethicists, and policymakers are necessary to establish guidelines and standards for responsible AI development. In conclusion, understanding the fundamentals of neural networks, from perceptrons to deep learning, is essential for professionals seeking to harness the power of AI. By leveraging practical tools and frameworks, implementing robust design principles, and addressing real-world challenges, professionals can develop effective AI solutions that drive innovation and efficiency. Continuous learning and adaptation are crucial in this ever-evolving field, ensuring that AI technologies are used responsibly and effectively to benefit society.